Okay. Bonjour. Hello. Okay. This is Masfun, and today I would like to present my rainwater basin in urban areas. How we do design rainwater basins in urban area. This is just simply a set presentation or lesson. So that's it. The content, there will be introduction and how we manage urban stormwater, and also the next will be how we do present the rainfall data and then design of a rainwater basin. That will be the content of my presentation. Okay, just to begin with the introduction, rainfall, when rain falls in the natural ground, in natural terrain, always there is a natural process. However, if we change the structure of the soil, if we consolidate the soil, or if we do asphalting, concrete, or anything like that, any artificial activity change the natural ground structure, therefore the rain that falls also affected. It means because of the increase in consolidation, the porosity of the ground changes. Therefore, the water which usually enters into the ground now turns into a runoff. That is the effect of artificial activities in a city. So whenever we build structures or build a city in urban areas, then we always change the structure of the soil. As a result, the runoff, the volume of the runoff changes, and it means the effective rainfall increase. So that is the effect of urbanization in the natural rainfall processes. And also, apart from decreasing or increasing the runoff, the percolation, because the percolation decreases, the groundwater water table also reduces. Normally, it is the rain that maintains the groundwater level. Nappe frappe, the nappe phreatic in French. And that level also will be affected because of the human activity and artificial activity in a residential area or in urban areas. The natural process of rainfall changes. For example, as we see it, according to the study conducted by the Natural Resource Conservation Service, that is in USA, a city which has an impervious surface of 70 up to 100% increases the runoff 50 to 55%. It means the rain that falls, the 55% of the rain that falls will turn into a runoff, turn into an effective rainfall. So human activity will definitely change the activity of the natural process of the rainfall. If we compare it with the natural ground, then only 10% of the falling rainfall goes as a runoff. So there is a big difference between the urban area and the natural ground surfaces. So that is it. So the second major problem in a city is because of the activity, human activity in a city, and also actually because of the increase of the volume of water runoff, the effect of the chemicals or those pollutions will increase. I mean, the pollution that goes into the river increases as well. Actually, the pollution caused by any activities of human being in a city, but as a result of the increase in permeability of the soil, the impermeability means of the soil, the effective rainfall increases. That also increases the pollution load of the effective the pollution load of the water that goes into the river. Therefore, there will be definitely pollution, and that pollution needs to be treated, or there should be some kind of methodology to treat the water that goes into the river. For example, in a river, in a city where there is a gardening activity, where there is a gardening, the fertilizers, for example, the residents might use fertilizer to their gardening activities, or pesticides, for example. The fertilizer contains nitrogen and phosphorus, which is a chemical that may affect the river life. For example, the phosphorus and also the nitrogen also affect the river life. For example, nitrogen most of the time you should mix it with oxygen and nitrite. It becomes a nitrite as NO3. Then the NO2 might, if that river, people might drink, or maybe animals might drink that water, and the water that contains nitrogen oxide, and that will enter into to the human blood vessel and might combine with oxygen, and you see that it becomes NO3, that will decrease the concentration of oxygen in human body as well. So that is dangerous for infants, for example, for children, where it reduces the oxygen concentration of the blood vessel. And then in a river, the algae might use that phosphorus to multiply itself, and the multiplication of algae in a river is not good for life in a river, because the algae compete with the fishes or other organisms to take oxygen. Then the concentration of oxygen in the river decreases, and then the fishes will lack oxygen, will be affected, suffocated, So that is not good for the organisms in a river. And there are also other pathogens and metals, for example lead and other sediments. Actually, the sediments may carry you see, phosphorus can't dissolve in the water, and nitrogen dissolves in the water. So most of the time the phosphorus goes into the river, or carried by the sediment. It's attached into the sediment and goes into the river. So sediment has to be removed from water that goes into the river. And also other pesticides, pathogens, detergents. There are a lot of chemicals and materials that are not agreeable, that are not good for human consumption or any organism consumption. So it should be treated. The water that we release into the river must be treated. Okay, you can see here that the oil from a car maybe or any other polluting industry, it might be, goes into the manhole, into the conveyance, stormwater conveyance system, enters into through the manhole and it goes into the river directly if we just simply release it directly into the river. And you can see as well the manhole is almost closed, half of it closed, and this might increase the temporary detention of water, and there will be temporary inundation around that area also. So manholes should be cleaned twice or in a year. Should be at least minimum one times in a year should be treated. And you can see the algae, because of phosphorus, the increase in algae causes the proliferation of algae itself, the increase in phosphorus. Then this algae will compete with the fishes and so on to consume the oxygen, and the concentration of oxygen decreases directly as a result. Then it will be, life will be affected in a river. So we should treat the wastewater that goes into the river. And how do we manage this storm that is created because of the human activity? Because we turn the natural soil ground into an impermeable surface, then the volume or the effective rain increases as a result. There is a problem. So how we need to manage this? How can we manage that? Because we know that we are preventing the water from entering into the soil. Then we need to create a permeable surface so that some of the water must be allowed to enter into the groundwater. We leave some kind of a space that is natural, and then the water can easily enter into the ground surface, allowing the water to enter into the system, the groundwater system. That drastically reduces the rainfall, the volume. So as a result, inundation will be decreased, and also other consequences. The methodologies are called low impact development strategies. These are the methodologies that we use to minimize the effect of urbanization. So for example, here we can see storm-based management practices. In a place of using some kind of conventional methods like any collection or any disposal methods, we use some kind of stormwater-based management methods. These are methods, very simple and very adaptable methods, but they do the job. Like for example, having a basin that might infiltrate the water or detain the water for a certain period so that it might infiltrate, and so reduces the peak. It reduces the peak. And also the other chemicals might be phosphorus or nitrogen in the water might be consumed by the plants, so that the water slowly be treated, like slowly treated, and then it will be released slowly, or it may evaporate, infiltrate, and so on. So this is a method, storm-based management practices that may be used to extend the time, the period of the runoff. The other methodologies that we can use are, for example, bioretention zone. This is a bioretention zone. A bioretention zone is a zone that simply just collects the water that is coming from the sewer system and just simply hold it for a certain period, and then the plants may use all those chemicals, nitrogen and phosphorus, and also facilitate infiltration into the ground, and also there will be evaporation, and then the water slowly infiltrate into the ground, and the rest will be released slowly. That also decreases the peak discharge, and also reduces the effect of the chemicals into that may affect the organisms in the river. So that is it. The others, for example, a green roof. Green roof is just, it says a methodology that simply we just plant grasses like this or any kind of plant above the roof, and the rainwater that falls can be intercepted for a moment and maybe used by the plant itself, or maybe it may evaporate after a while, so that this will tremendously decrease the effective rainfall, the runoff, so that inundation will decrease, the effect of pollution will decrease, and so on. The other is detention on roofs. That is a blue roof. It's called blue roof also. This is simply a container, many containers, just we can put them above the roof, and they simply hold the water for a certain period, then it will evaporate after a while, so it will be released slowly. That is it. And the other is the underground recharge structures, like this one. This will facilitate infiltration into the ground. The other is infiltration recharge basin. This is also give the water certain period so that it can infiltrate. So see, drainage canals like this one, that you see the water that drains over the canal also get a chance to infiltrate through. Unless otherwise it is important to have a concrete canal. It's better to construct the canal with a kind of rubbles like this one, so that most of the water will be allowed to infiltrate. That is important because it increases the water table, or it maintains the level of the groundwater, the water table, not phreatic. So as a result, it's good to maintain the natural structure of the earth itself, you see. Otherwise, most of the time, you see, when the water drains, when the water table goes down, the soil, the earth above it, it will collapse on itself. Yeah. So there will be a whole ground. Then that causes many damage. For example, if there are buildings around or any structure, that causes a problem also. That structural problem. So it is necessary always to maintain the ground water table. The level of the water table should be maintained as this is to its natural level, I think. It might not be good when the water table is elevated up. It will create a wetland, you know. That may also may not be good, but see, it is also not good to reduce it to a very low level, you see. So that is it. The other is constructing a pond retention basin like this one. Maybe it is a wet or kind of wet pond or a dry pond. It means a wet pond is like a dam, for example, which contains always water. And the dry pond is something like this one, which hold the water for a certain period and release it, just simply to reduce the peak discharge. That is it. That is how we manage the runoff in urban areas, so that we decrease the effect of its, like inundation and all those pollutions. Presentation of rainfall data. How do we present rainfall data? You know, we may have lots of many years of register or recorded data, rainfall data, for example. So how do we present it or put it in a manner that will be useful for engineers, for example? So for example, here the rain intensity, the duration of the rain, catchment area, return periods, and the frequency or probability of occurrence in percentage. All these things are important to design a reservoir, for example. Among others, there are many other factors we may consider to design a reservoir, but these are the most important parameters that we use. So we need to present them in a format, in a curve, so that many people can easily use it for design purpose. For example, we can say an intensity duration frequency curve, for example. Here we can see that for a certain period of rainfall, we can easily find the intensity of the rain, and for a certain return period, for example, 1 year, 2 year return period, 10-year period. A return period is a period where the rainfall event comes 1 in a 5 year, 10 year, 20 years, 30 years, 300 years, something like that. And for example, the average of it in a 5 year, for example, it may come now 2 years, 3 years, or something like that. But the average of the rainfall event that comes in a 5 year, its return period is called 5 year. And for example, the rainfall event that comes once in a 5 year has a chance of occurrence, 20% chance of occurrence in 1 year, for example. It may come in 1 year. There is a probability, 20% chance of occurrence. So that is the return period. And you see, these parameters are important always for design. For example, in a city where we are living, if engineers, if they use one standardized intensity, duration, frequency curve that may be developed by the city, municipality, or something like that, or any organization, institution that may do hydrology or something like that, and once they standardize it, then people can use, engineers can use it, so it will help for the consistency of the design procedure. See, they may calculate themselves, and they may see, they may calculate differently, for example, because of the different they use different methodologies and calculations. They might consider different intensity for the same structure, maybe. So that may, be good. So having all these curves will help for the design procedures to be consistent. That is like that. Hydrological graph is good. A curve that may tell us, for example, during the rainfall period, which amount of rainfall intensity occurs at what time, or something like that. For example, here at 8 hour 15 something like hours, the intensity is very high, so that we can see the distribution of the rainfall intensity in a period of time. So that is a graph. And also the precipitation bus curve, also that is the cumulative rainfall versus time in hour or minutes, and we can calculate from this curve, for example, the intensity just simply from the slope of the curve. We can find the intensity of the rainfall. And also we can see or learn from this curve that the distribution of the rainfall, the period, we can see, for example, the rain might come or falls intensively at the very beginning of the beginning hours. For example, at the beginning of the rainfall, it might be very intensive. Then it stops. It stops for 1 hour or 20 minutes. Again, it rains. Then it rains very, very intensely, for example. Or it may be, raining very, very slowly with a low intensity, and that will tell us the distribution of the rain in a period of time. You see, the intensity, the falling of the rain comes or was very, very strong or steepy and the first period of raining, and then no rain, then it continues like that. Then you see that will tell us that is temporal distribution of the rainfall. So that is it. That is it. These are the curves, among others. There are other curves as well, and these are important. This is just simply to show that how we present our rainfall data. It's not just simply we record them, but we need to prepare them ready-made for design procedures and so on. Stormwater basin, how do we design now? Or why we design it? Most of the time when we design or we build a residential area, obviously we just simply change the structure of the soil, consolidate, and permeability of the soil will be changed because of the asphalt, concrete. Also the consolidation process, change the infiltration and so on, then it will increase the runoff. The effective rain will increase. It means it might be, very little, or the effect might not be sensed if the area is small, but if the area is very, very large and continuous, then that will create or produce a lot of rainfall, runoff, effective rainfall. So this needs to be managed. Assume that this is the watershed area where we are going to build construct a residential area, for example, and this is the place where we need to build a detention basin. But before we build a detention basin, for example, here is the natural a river, and may have some structures like bridges and so on, and there might be here residential areas, for example, buildings here and here, something like that. Then if we increase the effective rainfall of the runoff, then the peak discharge increases, and that peak discharge may affect the structures at the downstream side of this river, for example, because the structures that are already constructed with a certain kind of peak discharge, when the peak now increases, it affects the structure. That structure may be unusable, for example. If there is a culvert, for example, the discharge might overtop the culvert, you see. So there is a lot of damage at the downstream side of the river because of the increase of the runoff. That is one cause. That is one case. Therefore, we need to reduce the runoff to the status where it was. You see, for example, if the maximum discharge was, for example, assume that 30 meter cube per second, it's just simple assumption, that is the previous discharge. Then now if it increases into 50 or 100 maybe, then we need to reduce the peak discharge into 30 to the status where it was, to the previous peak discharge value, so that we minimize the damage that may cause at the downstream side. This is one cause of the one reason why we build stormwater basin. In the other area, to increase the infiltration and so on, all other processes that we have discussed before. Those are the reasons why we build the detention basin. That is it. That is it. We minimize we increase or elongate the period for the peak to arrive at its peak discharge level, and we also allow the water to infiltrate or to evaporate so that it will be decreased in volume as well. As a matter of fact, the volume or the runoff volume that is coming from the catchment area may not be reduced because we build a detention basin. Most of the time, the purpose of the detention basin is to reduce the peak discharge. If it is actually concrete or something like that, an impermeable surface, then the volume might not be decreased as much as the peak discharge decreases. That is the purpose of the design of stormwater basin. So, okay. Here to show you. Sometimes we may build along the way something like this, a deep sump catch basin that might be used to catch some of the sediments and also some of the oil and the grease might be floated and separated. This is just simply a way of treating the water, storm water, just simply physically, and purifying it a little bit and releasing the water to the downstream side. That reduces the amount of pollution, but it might not completely remove everything in the water. If we need more treatment, we need to implement other infrastructures that may help us to treat the water completely, the chemicals in the water as well. So that is it. So how do we design a rainwater basin? So we need some data to design it. This is just simply an example. This is an example, simply a simple basin. Just simply build it with a concrete or it can be natural as well, natural surfaces. But the size of the reservoir is important, so we need to design that size. So how do we design it? We need to have some data, for example, hydrograph, inflow hydrograph, the hydrograph that is coming. This might be recorded at the spot. See, for a certain period, we just establish some kind of measuring device to measure the hydrograph at the entrance point. Or we may calculate it using some rational formulas, other catchment study formulas. For example, the water that is harvested from the catchment needs to be calculated from SCS curve method. There is a curve number method, that is SCS method, that is the methodology where we can calculate the volume of water, the runoff, and also the peak discharge. So in this we need to know time of concentration, lag time, and so on, infiltration, detention, evaporate. All these things are considered to calculate the hydrograph or the runoff volume. And also another method to just simply calculate the peak discharge using a rational formula, that is for small catchments, I think. So the other methodology is horizontal infiltration method also, that is to calculate the infiltration and also the runoff from the catchment. For example, in our case, the residential area is the catchment, the Basin Versa in French, and we need to calculate everything, the water coming from, and develop a hydrograph, that is inflow hydrograph. That is important, that is common or known, and we need it to design a rainwater basin. And the other is the surface area of the basin. For example, if it is natural, we can do some surveying work and develop a contour and calculate the change in volume in area. You see, there is an area here, an area here. Then we calculate the volume of the area, and we sum up. Then that will be the cumulative volume of the total area. See, so we need to know all those stuffs like contour and so on, and calculate the area and the volume. That is a known thing. We need to know that. And then we need to know, for example, if we are going to construct a basin in a concrete or something like that, we need to know all the size and so on, so that we will be able to, and we can calculate the outflow of the incoming water just simply using orifice or weir formula, and that is it. This is the important data that we need to. Then we can design our basin or stormwater basin. For example, this is the hydrograph that we have to design this basin. For example, everything is known. The hydrograph is known, the duration, discharge, and so on. The volume that is coming is known as well. We can calculate from this area. Then we develop elevation storage curve. How do we develop an elevation storage curve? We just simply develop elevation storage curve simply by relating the elevation and calculating the volume. For example, we have the area, surface area of 1 here, surface area of the lower surface area 2, and we can take the average of the areas, and there is a height between the two surfaces. Then if we multiply it, the average area multiplied by the height difference, then we can calculate the change in storage. Similarly, we do, beginning from 0 up to the top level, we can calculate the storage and elevation relationship. That is called elevation storage curve. This elevation storage curve will help us later to calculate, to route the inflow hydrograph into the outflow hydrograph. That is it. The second curve we need to have is the elevation versus discharge curve. We need to develop an elevation to a discharge relationship. What will be the discharge when the elevation of the water is this one, for example, because we have an orifice in a weir that the water may go through or fall over the weir. Then we can calculate, because weir is normally used to measure the discharge or flow. Normally weir also, it is easy to calculate the discharge of water flowing over the weir, because we have a formula to calculate that. And also it is easy to calculate the water that goes through the orifice as well. So we need to calculate, use those formulas and calculate when the head of the water is this. Just we use those formulas and calculate the outflow, and we develop a relation between the elevation and the discharge, and develop this curve. This curve also useful when we route a hydrograph from the inflow into the outflow. The third curve we are going to develop is the storage indication curve. Now this is very important. The storage indication curve is very important, and we relate this discharge that we have with this formula. For example, 2 times the storage in a change in time plus the outflow is just an equation. We develop a relationship between the two. This will be developed from the other curves, the one which we developed. We know the storage and we know the discharge from that curve, and we relate them. We relate with this equation, and later we are going to use that storage indication curve also to calculate the outflow hydrograph. So this is the equation of the storage equation, and developed from the that is conservation of mass equation, with the principle of conservation of mass. It means any water that is coming either will go out or stores in the storage. So when inflow is equal to outflow, then the storage is 0. Everything goes in, goes out, it means. So that is how we just simply calculate the storage in a reservoir. Based on this equation, we develop, we will arrive into this equation, so that will help us to calculate the outflow hydrograph. For example, I can show you how we arrived into this equation. Let me show you. Just for example, here it is. This is the conservation of mass equation, this equation, and assume that we have a hydrograph. This is the hydrograph of inflow and outflow hydrograph, just simply any hydrograph. Then you can see this is the inflow hydrograph most of the time, that is the coming flow. Then this is the outflow hydrograph. Then we can take a time period and a change in time, and we can calculate the average inflow and the average outflow, and replace it in this inflow. For example, this is the inflow. We can just simply take the sum of these two divided by 2, which is the average, and replace it here. And then here also the outflow n and the outflow n plus 1 also replaced here. The average of the two will be replaced here, and the equation will be similar like this one. And the storage will be this one, the inflow, the average inflow, and the average outflow. The average outflow, it will be the change in storage with this change in time, as the change in time t n plus 1 minus t n. So this is the equation, but now we can rearrange the equation in a manner that the norms at one side, the unknowns at the other side. So because we have the hydrograph, the incoming hydrograph, the inflow hydrograph is known. So inflow n and in plus 1 are known, definitely known. And the first outflow, this is a known outflow because it's 0. The first outflow is 0, and the first storage, this one is also Sn is 0 also. So the part of the equation at the right side is a known, it's a number. We can sum them and we can get a value for this, so that this will have some kind of value. This is the unknown part of the equation. We just rearranged it, and this one will be unknown, and the unknown has some value. However, we have two variables here. The storage and the outflow are unknown. So we need to solve this equation. We need to have some kind of methodology to solve one of the variables so that we can find the other. You see, therefore, here is the use of the storage indication curve. Now, because we have developed the storage indication curve with this equation, you see, with this similar equation, we can let us see the equation here. You see, with this equation against this discharge, you have a curve, so we can pick a discharge, for example, for a certain equation. The equation, as we have said, has value. We can calculate here. For example, for this one, we can calculate. Because we have the value, then we use that value to look for the discharge. Then, if we have the discharge, we can replace that discharge either here or we find out that discharge, you see. So now the variable reduced. Now the only variable we don't have is the storage. So we can go to that. See, now we can solve the equation. This means, for example, how we can solve it. We have this equation already from the graph. No, we have this equation, value of this equation from this And now we can go to the curve and calculate the outflow, the discharge, and we can reduce or subtract 2 times of the outflow discharge from this equation to find this one. This is a term used for the next equation, the next value. The next value will be calculated easily because we can replace this one into this, and the n plus 1 plus n plus 2 is also known. Now we calculate the next equation. The same thing we do again and again, repeat the same procedure, and that is it. That's how we develop a hydrograph, an outflow hydrograph. That is called a storage routing. I will show you how I calculated the storage, the outflow hydrograph, just using all the numbers and so on. Then you will know what I'm talking about. So that is it. That is how we calculate the outflow hydrograph. For example, here we can see here's the result. You see, this is the result. We developed the outflow hydrograph. This is a calculator, and this is the elevation of the water, and this one is the incoming known. This one is calculated using from the storage indication curve. That is it. So now we have the outflow hydrograph. We know the maximum discharge, the maximum peak discharge that we designed. So for example, if it was 0.29 meter cube per minute per second, meter cube per second, the discharge of the previous discharge, that might be less than that one or equal to the previous discharge, the status where it was, then our design is perfect. So we don't need any change in the well length or 50 meter and so on. We just simply adapt it as correct design, and that will be the design of the basin. If there is anything to change, we need to change the size of the wheel or the orifice. That's all. And we also know the volume of the water in the storage tank, for example, in the basin. This one is the volume. See, if you take the area of this, the area between the two hydrographs is the volume that is stored in the basin. So that is it. That's how we design a basin. Then I will show you how I calculated this is the first of all. Let me show you some other curve, infiltration capacity curve. For example, this is an infiltration capacity curve. That is very important when we use calculate rainwater from a catchment, for example. For example, if we have a hydrograph, for example, here, if we have a developed hydrograph here, for example, we overlap it with this one, and then we can just simply know this one, the area under the curve is the volume of water that is infiltrated. the area above the curve is the volume of water that is in effective runoff. That is how you get the graph cuts like this one. If you have like this, then the other is the runoff, the one below the curve is the infiltrated water. And this one is the curve I developed for intensity, duration, frequency curve. This is return periods and intensity with duration. So this will be helpful for the engineers. That is how I developed the rainwater bathing questions of the curves. These are the curves. You see the elevation is known from the contour and so on. The area is also known. It's very simple to calculate the area from ArcGIS or QGIS, and then we can calculate this is a conic formula actually. Conic formula, elevation 1, elevation 2, elevation 2 minus elevation 1 divided by 3, area 1 plus area 2 plus area 1 times area 2 square root of 2 areas. This is just simply a conic question, multiply them, you will find the volume, change in volume. Then when we add up all the change in volumes, that we will get the cumulative storage. That is the cumulative storage of the area where we are going to construct, or with the basin, that the one which we saw, and that is the curve, elevation storage curve. We developed it, we have seen it before, and that is important to later to develop a storage indication curve, and then develop the outflow hydrograph. Now elevation discharge curve, rating curve. See, the elevation is the same. The head of water, we just simply assume head of water. The head of water depends upon the elevation. You see here, just we can calculate for those heads the discharge. Debit means actually here is discharge. So we can calculate the discharge using the formula, the office formula that is given here. At the beginning, I just simply office equation here. Discharge is equal to the coefficient times the area of the pipe times the square root of 2 times G times H. H means the head, G means the gravitation, acceleration due to gravity. So using this formula, simply we can calculate the discharge. Same thing for the weir also. This is the formula given for the weir. We can calculate for the weir as well. So the weir begins at elevation 3260. Then the weir, then we sum up the two. Or see here 0, 0, 0, 1, 0, 0, 0. Then no, this one is the weir, or the head starts here, and we sum up or this is the total discharge that we have in the basin, from the basin. That's the combined outflow of the office and the discharge of the weir. discharges beware. That is it. After that, we have the inflow data already. It's just simply given when we calculate, and from the calculated volume storage, cumulative storage, and from the outflow, that's the cumulative outflow that we have seen here. Then we can develop this one, this equation is to change plus or with a cube. That is storage here. The time is just like the inflow hydrograph, 10 minutes difference. Changing time 10 minutes. Storage is here plus the outflow is here. Calculate this one. Now we can, this is this part of the table will give us the storage indication curve. That is very important to calculate the outflow hydrograph. Now, as I told you, this is how we calculate the inflow and outflow, the outflow and the elevation of the hydrograph, for example. For example, as we said, the value of this thing is 0, because it is known, and the value of the first inflow is 0, and the outflow is also 0 at elevation 30.48 meters. Then now I1, I2, when I1, I2 is this one. Then, as we have seen that in the equation here, one step, the other equation is one step back. You can see here, you can see it here, you see, this is in plus 1 plus is always the first row. This is the first row, or one step back it means. Then we can add these two and we will get one step in advance. It means n plus 1, n plus 1. You see, from these equations we will find this one. For example, this might be a second row. The result is in a second row, but this one is in a first row. It means, as you can see here, for example, I1, I2 is this one plus this one in the first row, but because that is n storage, see, this one changing storage, n is 1, you see. Then the result, when we sum up, the result we find is this one, 2s plus o, 2s changing time over changing time plus o is this one. Then once we found this equation, we can see here in this formula, once we found this equation, we can go to the storage indication curve and look for the discharge. We see, we go here, let me show it again, storage indication curve. Once we found this one, we just simply look the discharge and pick for the discharge from here, and now we calculate 2 minus the discharge. Is like this one. 2 minus the discharge that we found from the curve will give us this equation, n plus 1, n plus 1. That will be the substitute in the next row. It means we'll take this one and replace it here. By the time when we replace it, this one will be 2 n plus 2 n plus 1. That will be the next equation. So similarly, we continue in the same manner to calculate the whole row, all the rows calculated just like that. This one 2 times the outflow minus this one will give us this one. See, this one is 2 times minus the outflow. This one is R 120, and this one minus 2 times this one will give us this one. You see, give us this one. Similarly, the same thing. We continue until the end like that, and later we will find the outflow hydrograph, complete outflow hydrograph. And this one will be the maximum discharge at the elevation of this, and the period, the time is 90. For example, you can go and see the result. This is the result. This is the timing, for example, 90, maximum discharge. Voila. We designed our basin now. We have all the discharge and the elevation. Now it is easy to build the basin. That's how we design a rainwater basin in urban area. Merci beaucoup for listening. I hope it may benefit you maybe. So thank you for listening. The next lesson will be catchment studies, catchment calculation, and how we calculate the inflow hydrograph, and other stormwater design, or how we design a stormwater, the canal itself, and other hydrological and hydraulic designs. We will continue for the next time I will come with that. Thank you very much for listening. Over.